Hello, this video is about simple harmonic motion and oscillations. Now, there are two conditions for simple harmonic motion. The first one is that the force acting on a body is proportional to the displacement from the equilibrium. So therefore we can write that as the force is proportional to the displacement. And in this diagram here, I have a body showing that rectangle there, fixed between two springs, the springs being attached to either side to two walls. And its equilibrium position, where if it wasn't moving it would remain still, is in the middle there. And at the moment it is oscillating in between a maximum amplitude A and a minimum amplitude minus A. And at this instant in time, it is the centre of it is at a position x, displacement x. So, going back to the definition, so for simple harmonic motion, the force must be proportional to the extension, and also the force must act towards the equilibrium position. Okay, so if we look at this diagram here, as you see, this spring is stretched, this is compressed, so the force would be acting here towards the equilibrium position. And of course, when the body is on that side, again, the force will be acting towards the equilibrium position. Now, with springs and Hooke's law, we can say from Hooke's law, we can say that force is equal to the spring constant times displacement, and for simple harmonic motion, because it is acting in a negative direction, we write that force is equal to minus kx. This produces an acceleration towards the equilibrium position, so there, little a, is the acceleration acting towards the equilibrium position. Now, the maximum velocity will occur when x is equal to 0 and it's passing through its equilibrium position, and the maximum acceleration will occur when it is stopped, still at the maximum amplitude in the positive direction and a maximum amplitude in a negative direction. And the oscillation, one complete oscillation, if we start from where x is 0, will be all across to the maximum amplitude, back again, and then back through there. That will represent one complete oscillation. Okay. The motion of an oscillation body will be as a will be sinusoidal. So if we plot the displacement from the equilibrium x against time period, now time period, we'll get a curve like this. So when t equals 0, x equals 0. This is our established idea here. So, and at this point here in the cycle, we'll have the maximum displacement, which will be the amplitude positive A. This position here, we'll have negative A, which will be the other oscillation. So we start in the middle, it goes to maximum in one direction, back to the middle, negative amplitude in the other direction, then back to the start again. So that represents a complete cycle t. So that will represent t, complete time period, time for one oscillation. This will here halfway through is time period divided by 2, This here is time period divided by 4, and this will be 3/4 of the time period. Time period is the time for one complete oscillation. Now the frequency of oscillations, f, is the number of oscillations in 1 second, which is equal to 1 over the time period. Now we can also model this as looking at the phase in its cycle. So again, we'll model this very similar. I'm trying to make an identical curve if that's possible. So take that down, and that down. And what we will see is exactly the same curve I'll draw underneath, but that is certainly not the exact same curve. So that's better. Now, instead of looking at time period, we're going to look at theta, which is the phase in radians, or if you like, the phase angle. So the complete phase would represent 360 degrees, so therefore that's 2 pi for a complete cycle and pi for half a cycle. This is going to do with the phase, or the phase angle. And another idea we have is something known as the angular frequency, which is omega. And the angular frequency omega is equal to the number of radians in a complete cycle, 2 pi multiplied by the frequency.